In lesson 2, we're going to continue talking about generating equivalent expressions. And again, equivalent, we're looking for equal expressions. We're looking to rewrite things, simplify them. And in this one, we're going to focus on inverses, our additive inverse. It says additive inverses have a sum of 0. So basically what additive inverses are opposites. Why we have another name for them? Well, there's probably some good reasons, but I know we have additive inverse and multiplicative inverse, so we can talk when we're solving equations about using inverses. But it's really a lot of what opposites do. What do we do with additive inverses? And let me show you what that means here. I deleted a bunch of rows, so the first one isn't completed for us. If we have an expression of 3, that's an expression, no equal sign. The opposite of 3 is negative 3. Okay, so proof of opposites. This is where we come into play with additive inverses. If we have 3 and we add it to its opposite, negative 3, the sum is 0. And that's an important concept for additive inverses, for opposites. So if we look at the next one, our expression is negative 7. The opposite of a negative 7 is a positive 7. But what does that mean in terms of being an additive inverse? Excuse me, if I have negative 7 and add it to a positive 7, they equal 0. Okay, and we're going to be using this idea for simplifying. We're going to be using it when we get into solving equations. The same is true even if the expression isn't an integer, isn't a number, it's a variable. Remember, that is a number. It's a symbol representing a number. So the opposite of x would be negative x, okay, because however many units away from 0 x's, it'd be the opposite direction. Now, if I add them together, guess what happens? You still get 0, okay? What now if our expressions maybe look a little more familiar to how we think of expressions? What is the opposite of x plus 3? Well, the opposite, and this is going to be a big idea with simplifying today, it's not just the opposite of x. What we don't want to do is we don't just want to write this. Because that's like saying, hey, you know what? The opposite of x plus 3. No, it's the opposite of the whole thing. So I either put it in parentheses or I think of it as if it's the opposite of x plus 3, it's the opposite of x plus the opposite of 3. Okay, and this is how we're going to have to start thinking about things now. So if I add it together, I want to write it this way. If I have x plus 3 and I add that to the opposite of x, or negative x, plus the opposite of 3, or negative 3, how do we simplify that? So think back to the other assignment that we just did. And we can change, well, I'll change this around. We can change this order, right? Commutative property says we can change the order. And this becomes x plus negative x plus, I switch these around, 3 plus a negative 3. Well, x plus a negative x, they're opposites. They add to 0. 3 and a negative 3, opposites. They add to 0. So guess what? This all just equals 0. Okay, so anytime you have your opposites, your additive inverses, it equals 0. Now, that's additive inverses. What now about multiplicative inverses? Multiplicative inverses are reciprocals. Okay, reciprocals. Flipping it, right? It says find the multiplicative inverses in the first column. Show that the given number and its multiplicative inverse have a product of 1. Product means multiply. Okay? All right, then we're going to do some work with it. Okay, so in this case, be careful. We might want to write a negative 5 here, but it's not. If we're given a 5, its multiplicative inverse, its reciprocal, is 1/5. Remember, we can put a 1 under this 5. It doesn't change the 5. Now it says proof, show that their product that's multiplying is 1. So if I go 5 or 5 over 1 times 1/5, you can multiply straight across, right? 5 times 1 is 5. 1 times 5 is 5. What's 5 divided by 5? 1, right? You can think of it as cross-reducing. 1 and 1 have a common factor of 1. Doesn't help us there. But 5 and 5 have common factors of 5. 5 goes into itself 1 time. 5 goes into itself 1 time. Get to that 1 any way you think about it. So now it says use each inverse to write its corresponding expression below in standard form. We tend to get really wordy here. Let's simplify 65 plus 5. No, 65 divided by 5. Now don't just type it into a calculator. Let's think of it in terms of having an inverse. This we can rewrite as 65. Instead of dividing by 5, we can think of it as multiplying by the reciprocal. If we think of this as a fraction, dividing by a fraction is the same thing as multiplying by the reciprocal. I know you're like, well, why wouldn't I just divide? You would, but we get the variables down here, okay? So again, if you're looking at this, you can multiply straight across, and if, or you can think of it in reducing. 1 and 1 have common factors of 1. Great, but doesn't help us. 65 and 5, though, 5 goes into itself 1 time. 5 goes into 65 13 times. So this becomes 13 over 1, or just 13. Okay? How about this -2 here? Again, it's multiplicative inverse. If we put a 1 underneath, becomes 1 over -2. Don't make it positive. That's only when we're dealing with additive inverses and we're dealing with positive and negatives, okay? This one we're just basically dealing with multiplying and dividing. And the reason it has to say negative is because if I go -2 over 1, and I'm doing their product here, times 1 over -2, it honestly doesn't matter where that negative falls, if it's at the top or the bottom, because a negative times a negative is going to be a positive. And if you look here, whether you cross it out, cross reduce, -2 over -2, doesn't matter. It works out to be 1. Okay? Negative times negative is positive. That's really important. Another way we can think of 8 divided by -2 is think of this as a fraction. Not 8, 18, sorry. We can think of this as 18, or 18 over 1, times the reciprocal. Right? Dividing by a fraction is the same thing as multiplying by the reciprocal. And think of it as a 1 over a negative. Okay. 1 over a -2. Now, when you multiply straight across, a positive times a negative, positive, negative is going to be negative. And if you want to cross reduce, 2 goes into itself 1 time, 2 goes into 18 9 times, it becomes a -9. Okay? Now the reason this is important, because I know you're like, why wouldn't I just divide? Why do I have to think of it as multiplying by the reciprocal? By its multiplicative inverse, is because when we start dealing with fractions, the reciprocal of 2x is just like it was up here, 1 over 2 times x. Now if we want to prove this, that's the same as well. 2x over 1 times 1 over 2x. That works out to big old 1, all right, or little old 1, however you want to think about it. Okay, but right here, we can think of this as 12x over 1. Instead of dividing by 2x, think of it as multiplying by 1 over 2x. So when we go to reduce this, I want you to see that, again, 1 and 1, common factor 1, doesn't do anything. But over here, notice that they both have an x. That x crosses out. If you have x on the top and x on the bottom, they cancel out to 1. They divide out to 1. And then we can think of this as well. Or you can think of it as 2x goes into 12x how many times? Well, 2 goes into itself 1 time, or 1x. That goes into 12x 6 times. Okay? And whether you go 6 times 1, you get 6, and 1 times 1, you get 1, you get 6 for your solution. Okay? So what we're going to be dealing with now with generating equivalent expressions is we are going to be working on simplifying, but using that idea of additive inverses and multiplicative inverses.